Hi, welcome back my steel design friends. In this video, we're going to be talking about a generic design methodology for tension members. Unlike analysis where often you know the member size and the number of bolts and the number of holes and can compute a capacity, the more common problem in structural design is I know the loads and the length of the member, but I know nothing else. And so in order to get a first guess at a preliminary size so that we can fix our structural model, we need to have a methodology in place. And that's what I'm going to show you how to do today. So without further ado, let's get started. In structural design, we're faced with kind of a dilemma for selection of member sizes. On the one hand, I need to know a member size in order to be able to build a structural model and to get loads or internal forces on this member. But I can't do that if I can't get the member size if I don't know the internal forces. So the question becomes, where do you start? All right. So what I'm going to do in this video is we're going to spend a little bit of time. I'm going to outline a series of steps that I go through personally to kind of help design, try to eliminate some of the iterations that may be necessary whenever we get into trying to design a member for, in this case, a tension load. All right, so the first step that we do, we've got to come up with a first guess. Okay, now the things that we know in this is I got to know PU or have some idea of the magnitude of the load. Is it 10 kips or is it 200 kips? What's the difference? You know, there's a vast difference in the sizes that come out of it. Now, a difference between 150 kips and 200, not so much. But we'd like to try to be close on this, even if I'm not exact, because again, this number will be ever changing based on external loads on the building. Okay, and so, or whatever structure it is that you're working on. So if, you know, depending on relative stiffnesses and the way the building is framed, a lot of that is changing. So we're going to go under the assumption that we have an idea of PU, as well as knowing something about the building geometry. And generally, you have to know that. You know, how far apart are the columns, how tall is the floor height, where is the bracing located, things like that I've got to know, okay, or at least have made some decision, and otherwise this whole process is kind of a moot point. All right, so for me, whenever I start on this, if I know that information, you know, I've got the architectural drawings, I've got kind of a guess of how much load is going to be on that, whether it's from experience or whether it's from preliminary analysis runs using computer software, whatever the case may be. You know, I've got that. So the first thing I need to do is I got to come up with a first guess, and this is how I propose to come up with this. Okay, the first thing that we look at is we size the member for gross yielding. All right, we've talked about in previous videos that gross yielding is kind of a theoretical maximum on our capacity. So if I know from LRFD that my formula is phi-PN is equal to phi AG-Fy, phi is 0.9, AG gross area, Fy is yield stress, then I can take an estimate of the capacity of this member. And as long as this is greater than this, then I should be able to, you know, have a safe member for gross yielding. And typically this is the upper bound limit. Not always, but it's a good guess on the maximum load that a particular member size can get. So what I can do is I can take this formula and I can rearrange it in terms of A and make A a selection criteria. So if I do that, I get phi-PN over phi-Fy. Okay, again, that's just rearranging this formula, solving for AG. And then if I know that, you know, at the very least that phi-PN needs to be equal to PU, you know, hopefully it's more than that, but at the very least, if I use PU and I do an equal sign, then this becomes a minimum value. Okay, and then the other criteria, so that's how I kind of get a first guess on our strength parameter. Okay, for serviceability, which is deflections and vibrations and non-strength related issues for tension members, we have the criteria that L over R has to be less than 300. Well, kind of in a similar fashion, if I know where the member is and I have a guess at its length, I can calculate now an R minimum by taking this formula and rearranging. So L is measured in feet, and then I've got 12 inches per foot, and I divide that by 300, will get me two parameters that will give me a guess into some selection criteria for a member that might possibly work. Okay, but I have to meet both of these minimum requirements. So in some cases, RMIN will control, in other cases, AG will control. Typically, this controls when loads are small, and this controls when loads are very big. Okay, so that's kind of how I take my first guess at this. Now, like I say, I'm going to go through the procedure here, and at the end, I've got kind of an example problem that kind of shows how this works, and then we'll show you some other other methods that we can do just to kind of speed up the process. I don't want to be doing, doing a design for hours on end when I can get in and get out fairly quickly and have a very good first or second guess. Okay, all right, so now we move on to some information that we really haven't covered in this series yet, but it does start to play a role. Unfortunately, the design of tension members, as you know, we're looking at things like gross yielding and net fracture. Those two parameters are, well, the net fracture especially is dependent on a lot of information relative to the connection details. Okay, and this is where things get a little fuzzy, okay, because we don't know the number of bolts that we need. We don't know the size of the bolts that we need, and so forth and so on. But we can, I can show you some, even without understanding theory, I can show you some, again, some techniques and rules of thumb for first guesses into, a common normal building of structural bolt sizing. Okay, so the first thing I want to look at is I want to look at the quantity and the size of the bolts. Okay, now for shear connections, which is most typical connections for bracing, using a member and a gusset plate, okay, that's the type of connection we have as a shear connection. There's a table that we can look at in section 7 of the code, and when we do our videos on bolts, we'll spend a lot more time on where these numbers come from, but for now we can just kind of jump in and take a look at table 7.1. This is on page 722. Okay, now without getting into a lot of what these are, the most common bolts fall into group A. These are the A325s, and then we can look at kind of some sizes that are kind of common for structures. Okay, and typically in normal buildings, 3/4 inch is about as small as you'll go, for typical structural load. So if I take the worst case, that is a single shear bolt, okay, with threads included, I'm looking at somewhere around 17.9 kips per bolt, okay, for each bolt in shear. And so I can use that to then get a guess on the number or the quantity of bolts that I need to have in my system, okay, and with that, then we can start playing some games relative to how am I going to lay this out. Okay, so that's kind of, so I'll use this number often as kind of just as a first guess is to get a sense of, do I need 4 bolts or do I need 16? Okay, big difference, and how I lay this out can dictate things like where are the bolts located, do I bolt the web of an I-beam, do I bolt only the flanges, all those kind of things start to factor in to our selection. So we'll take 3/4 as a first guess. Okay, and again, that's a lower bound. If you find out you have a problem, you may have to come back and bump up your bolt sizes in order to get the numbers down. But just again, as a first pass, a 3/4 is kind of a good rule of thumb. All right. Okay, so again, we're looking just at shear connections. If you have a tension connection, you can do the same thing over on the tension table in 7.2. Okay, so we'll set this aside. Okay, and we'll come back and kind of eliminate, look at what we have happening here. All right, so now so our rule of thumb here says we're going to take 3/4 inch diameter bolts, and that can carry, the book said 17.9, I just use 17 kind of to give myself a little bit of extra room on there. This gives me a sense of the number of bolts that I'll need. Okay, now if our theoretical maximum capacity we declared up in step 1 was based off of gross yielding, phi PN was phi AGFY, I can set that equal to, for the connection, the number of bolts multiplied by what would be, 17 kips per bolt on this. It's kind of a guess. Okay, so that's what we're going to kind of do. Now, again, you're allowed to, if you want to do a smaller number, you can, just to get a sense. Whether it's 15 or 17 doesn't really matter. I think I kind of go back and forth sometimes. A little bit is played off on experience. Okay, but for us, we can go in and we can do this calculation. Okay, so the number of bolts then is phi PN over 17 kips per bolt. Okay, so you'll get a number like 10.2. Okay, so maybe what I need, obviously you can't have a decimal number of bolts, so at the very least I need to round to 11, but sometimes I'll round up even higher in order to have a pattern that works, for, say bolting of flanges on an I-beam, and I'll show you that in an example. There's a little bit of a rule, but at least you have a sense now. Is it 2 bolts or was it 22 bolts that you needed on there? Because that will kind of dictate, the length of the connection and the geometry and how we can lay things out, which then dictates, parameters that help us with our shear lag coefficient, which we'll need for net fracture. Okay, now, some preliminary arrangement of these bolt questions that are kind of in the back of my mind are as follows. For W shapes or wide flange shapes, am I bolting the flanges? Okay, should I bolt the web? Should I bolt both? Okay, typically, if you remember the shear lag table that we talked about, and if you don't remember that, go back and look at the video for our shear lag coefficients, table D3.1. Typically flanges, if you bolt the flanges of a member, you get a higher U value than if you bolt just the web. Okay, and if I bolt both, then maybe I can use case 2 or even case 1 to some degree to kind of play with it. But, one or the other, the flange is generally our first option for bolting and seeing if we can make this work. So again, we're looking at table D3.1. Now, with that being bolted, this is why case 7 in the table exists. So again, I know we're bouncing around a lot here, but we've got to understand our basic, in our shear lag coefficient, we're looking down at, this is table D3.1, we're looking at either case 2, which is our general formula 1 minus x bar over L and the rules for calculating that, or we're looking down at 7. And this is why 7 exists, is because there are 2 scenarios that exist if you have a WMS or HP. These are the, the flange beams types of shapes, okay? With flange connected with 3 or more fasteners per line, I can quickly see that U is 0.85 or 0.9, okay? Whereas with web connected, I can see that U is 0.7, no ifs, ands, or buts about that. Okay, so this is why those 2 rules exist, is that I can take kind of some first guesses. Typically, as you can see, bolting the flanges gives you a stronger connection for net fracture than bolting the web does. Now, again, as we're talking about this, recognize that we're only looking at the net fracture case. We're not considering other phenomena like block shear or slicer or bearing or things like that, because as you'll see in the videos when we get to those, we have more control over that layout about spacing and those kind of things. I'm just looking to see, can I get these bolts laid in a certain fashion, and where can I put them, and what maximizes my U value, because this will result in a smaller member size. Okay, so that's why we're looking at flanges or webs and answering that question right off the bat. Maybe there's a reason you can't bolt the flanges, okay, or maybe there's or a reason that you have to bolt the web. That can dictate those as well. Those are all factors that will kind of come in and play, but that's what we're looking at on our D3.1. Okay, all right. So that's how we look at W shapes. Now, what about angles? Okay, well, the question becomes, for a member, do I need to do one leg per bolt, one leg bolted, okay, which will give you a lower U value? Can I bolt both legs, which requires some extra details? If I have a plate on the back side of this thing to accommodate those, I also need a plate here to pick up the bolts and the flanges. That's 2 plates. That's kind of a more complex connection to make. Okay, so if I can get away with just bolting one flange, it's a lot easier. Okay, so those are all things that I'm thinking about. Again, you may not have the answer to these questions, but at some point you got to start making some decisions on this. The other question is can I get multiple gauge lines in there? And you can use the AISC minimums, to kind of figure out, well, can I physically fit 2 bolts in one leg? Okay, now the typical rule of thumb is that you set this gauge line spacing at 3 inches, okay, and then if I have 1.5 inches here and I have a 2.5 inch here, you're looking at somewhere around, the only way I can get 2 of these is if I have a leg that's longer than 6 inches, and even that's kind of pushing it. So you have to have a really big angle or a really big member to be able to put multiple gauge lines, into an angle. Okay, so those are some of the questions that I'm looking at with regards to angles. Okay, typically, we're looking at, that we're looking at. Like I say, it's an L6. It's kind of the classification here. Again, rule of thumb: use 3-inch spacings between these, in both directions, and that's a fairly typical standard for construction for bolt pattern spacings, and that starts to give you kind of if you make that assumption of 3 inches up here, now I can start taking a guess. If I know how many bolts I need and I know I need 2 rows, you can start getting a guess on, well, 3 inches plus 3 inches, this connection would be 6 inches long. You start getting a guess on what that L parameter is, which allows you to come back into case 2 if you need to. All right, so that's another thing that we're kind of looking at in the tension design. Okay, now we're into the game of let's estimate our shear lag coefficient. Okay, again, this is table D3.1. I just showed that to you. Okay, and so the things to remember here is that we can use 7 or 8 to kind of get, wherever possible, to get us a very easy, quick guess at the particular size. But remember, the small notes at the bottom of case 7 and 8 of this says that if U is calculated per case 2, the larger value is permitted to be used. So I can't go back up and do case 2, and if case 2 ends up giving me a larger value, I'm allowed to use that. But what we can do in design is I can say, well, I'm willing to live with this, and I don't care if this is larger or not. At the very least, I will be this value, okay, even if that's the worst case. Okay, so because of the comments in both 7 and 8 both have that same statement. So I can use these as kind of a lower bound guess on you, and then again, we're just looking for kind of getting a sense of the size of a memory that we're needing to be able to do that. Okay, all right. So that's kind of where we're at on that. Okay, so we'll use case 7 or case 8, whatever the case may be. Okay, and again, sometimes it's a good guess and sometimes it's not. Okay, once I have that U value, now I can start kind of getting a guess on the effective area. Okay, so we've chosen a member based off of AG min and R min. Okay, once I have that, now I can come in and I can calculate the effective area, because you do have to check net fracture on this. So if I rearrange my formula a little bit, we know effective area is U times AN, that's going to be U times AG minus A holes. Okay, now what we'll do to get the effective area is that we'll use the thickness, the area of the holes we know is the diameter of the hole multiplied by the thickness of the part where the hole occurs. So we'll use the T that comes out of our guess from our GY calculation. So for, if the bolts are in the flange of a beam, we're using TF. It's the web of a W section. It's the, TW. If it's, through an angle, we're using the thickness of the angle. All can give us a guess on this. Okay. And then we can use that to calculate our area of holes. And then I know A gross from step 1. I've got a guess on area of holes. Okay, now the thing that we do have to look at is we have to figure out, well, in our net fracture plane, again, if we come back and kind of look at our graphic here, our net fracture plane would be coming through here. And we're looking at, well, how many holes lie on that plane? Okay, so in this case, if I bolted both legs, I would have 1, 2, 3 bolts on it. Okay, we're going to assume all the bolts are the same. That's typically a valid assumption. Okay, over here, if I look at net fracture, it would be 2. If I only bolt one leg, it would be 1. So you've got kind of this preliminary layout that you're looking at, and it gives you a guess on the number of bolts on a plane, which then allows you to take a guess at the area of the holes. Okay, and so that can kind of do. Now, AISC, there is a check that, that you can perform that will quickly tell you if net fracture controls or gross yielding will control, and that's by setting the equations for net fracture and gross yielding equal to each other, that AE over AG greater than or equal to 1.2 times the ratio of the yield stress to the ultimate. Okay, well, if this is true, then gross yielding controls. If it's not true, then net fracture controls, and you've got to kind of iterate a little bit more. It's a very useful check, and you'll find this on page 8-2 of the specification. So if I flip over to that one real quick, I'll show it to you. Sorry about that, I lost my index page. And that is not the right page. Well, give me 1 second. All right, sorry about that. That should be 5-2 because section 5 is the tension section in the code. So here it is. Okay. So again, what this is, this has some handy tables, which I'll show you how to use a little bit later in the video. Some for what would be available strength in axial tension, and I'll show you how to use this table in just a moment. But the check that we're looking at is this guy right here, this equation 5-2. Okay, because we know these are your LRFD requirements. There's the gross yielding requirement. Here's the net fracture requirement. If I rearrange this ratio, well, the grade of steel, so this side, and I've chosen AG off of the GY calculation initially. All I have to do is check what is my AE value, and I can very quickly tell you whether or not this is a gross yielding failure or a tension failure based on the number of holes that you're putting into it. So that's kind of a neat little trick that's not often expressed in your average textbook, but it is pretty convenient to be able to find that. Okay, all right. Now again, like I say, I apologize for the page issue. It's just that this is one of those formulas that I've known, that it's in my mind that I know this ratio, this 1.2, to be able to calculate it, but this is where it's coming from. All right, so now what we do is we have to go in, and so if you find out that gross yielding is the controlling factor in this, well then you're done. You've got your size and you're good to go. If you find out that it's not, then I need to come down and we've got to make a guess on, well, what do I need for an AG minimum from net fracture? Okay, so we're going to kind of play the same game, but now we're going to use the net fracture case on this, and this is phi PN is going to be equal to phi FUAE. So this is equal to 0.75 FUAE. Okay, and I know that if I rearrange this for the area effective on this, that this is phi PN over phi FU, which this is PU over phi FU. So it's just the same game that we played back in step 1 of our methodology. And now I can rearrange this a little bit and say that this area effective, okay, because we know that area effective is U times A gross minus A holes, okay, that I can solve for A gross in this formula by substituting in this equation and solving for AG and get an expression that looks something like PU over the shear lag coefficient U times phi times FU, okay, plus the area of the holes. Now again, the area of the holes, remember, is the sum of all of the holes on that plane. Okay, so you would know if you're bolting flanges and webs, these thicknesses can vary, but it's just kind of the, if I have 4 flange holes, then there are 4 bolts, and the thickness is TF. If I have 4 in the web or 4 in the flange and 3 in the web, well then this guy will change based on it. So you've got to go on a hole by hole basis as you look at this. But this is a pretty good guess, right? Because I know PU, I've got a guess on the shear lag coefficient, I know phi, I know FU, and we've taken some guesses on a preliminary layout onto this A holes calculation, okay? Now, if we go through and we look at these calculations on here, if my AG minimum, for net fracture is less than my AG minimum for gross yielding, okay, then we're okay. The AG min controls. And this is what that check that I showed you, this rule of thumb up here, will prove to you, but you can also check it this way. Okay, otherwise what we do is we take this AG minimum, choose a size that goes along with the R minimum, and then we go back to step 2 and come back around. And it's kind of an iterative process, a guess and check when net fracture controls. Because a lot of the variables depend on how is that connection laid out, how many bolts do I have on a given plane. Okay, so if you're having a problem meeting the net fracture capacity, maybe instead of doing 2 gauge lines, I only do 1. Or maybe I go, instead of using 1-inch bolts, I go to 3/4-inch bolts. There are some things that I can start to do. Or maybe I go to a double angle connection instead of a single angle connection. Everything that I can do in order to be able to try to get this number up. Okay, but that's the iterative process that kind of some of the thoughts that are going on. Now I know it's not real clear, and as you do more of these and get more experience, you start to get kind of a sense of what the values are doing, and you can kind of head out, get a feel for what's going to control, and like I say, with some of the tables. But just for practice sake, let's just give one a shot here. Let's suppose that I have a member that is 20 feet long, and it has an axial factored load of 200 kips. Okay, we want to find the lightest W shape of A992 to do this, and this will kind of illustrate the methodology that we're going to look at. So the first thing we do is we calculate the gross yielding and find AG minimum. So I'm going to take PU over 0.9 over 50. Okay, again, that's my FY. Okay, and if I do that, this says that I need 4.44 square inches of steel as a gross area minimum in order to be able to account for 20 kips in gross yielding. Okay, and then I also look at the serviceability criteria at the same time. L over R less than 300. Our R minimum then is 20 feet. That was the length of the member multiplied by 12 divided by 300 tells me I need an R minimum of 0.8 inches. Okay, which for an I-beam, we know RY will control for a W shape. Okay. Okay, now if you're doing some other shape, then that may or may not be the case. So, if it's a built-up section, you got to be careful. But your minimum for just a standard W shape will always be RY. So we're looking for that as we start to go kind of shopping for those particular shapes. So if we flip up to table 1.1, okay, what we can see is we're looking for an area that is somewhere that is 4.4 inches squared or larger, and an R that is 0.8 or larger, an R minimum on this. So if we kind of look, one of the ones that leaps out at me is an 8x15, and that's just kind of a fluke. I managed to hit one with exactly that area. Might be a little bit hesitant to use it, but for now, just for the sake of this exercise, let's say, okay, let's try an 8x15. And so if I come over and I look at the 8x15, if we look at our R's, we're looking at the RY column, our number is 0.876. This guy works. Okay, he meets both of the criteria, so he'll be a good first guess for us to try. So we'll try an 8x15. Okay, and so that will meet the gross yielding and as well as working on the slenderness of those. All right, we'll get that book out of the way. Okay, and so that will be our guess. Now, all I've done then is I've chosen an 8x15 as my guess. I've gone ahead and written down all of the section properties that I'll need as we proceed through the rest of the problem. I've got the depth, the flange thickness, the web thickness, TW, AG, RY, and ZX. All of these will come out of here and will be used as we move through the process. Okay, all right. We're going to estimate our bolts. Okay, so if we assume 3/4 of an inch diameter, A325N at 17 kips per bolt, then the number of bolts that I would need to support my 200 kip load on this, okay, would be 200 kips divided by 17. I would need 11.76 bolts. Okay, in which case I'm going to round that up to 12. And again, we got kind of lucky in this, you know, and I didn't plan it this way, but the 12 bolts is actually a nice number because it's divisible by 4. And I know that for an I-beam that if I bolt into the flanges, you have to bolt 4 locations. Okay, so what that means is that my preliminary layout, if I do a flange only connection on this thing for a W8 on here, then I could end up having 3 lines of flange only bolts. Okay, another possibility is that you could do this, bolt the flanges, but then also put 2 in the web. And you can kind of look at, well, would that work, you know, in the line? And in this case, I would have 6 bolts per line. The problem is, you know, and then 6 here and 6 here, that gets me 12 bolts. It would be a much shorter connection. Okay, the problem is that it's a little tight to try to fit all of this into an 8-inch depth, right? If this is 3 inches, that leaves me 5 inches from here to here and here to here, you know, giving me 2.5 inches, if you will. That's a little bit tight on this, so that's why if I can avoid the web bolting on this and go only with the flanges, then I'll get a higher U value for this. Although this would give me a higher U. This U would probably be a 1.0. The other problem I have, though, is that now instead of subtracting 4 holes from the cross section, I'm now subtracting 4 plus 2 more. I'm turning this thing basically into Swiss cheese. Okay, and subtracting these areas out might hurt me on my selection of the W8 by 15. So again, there's some play in this, and sometimes you get lucky on the guess and sometimes you don't, but those are all thoughts that I'm looking at for working on this. But for now, we'll go with 12 bolts. I'm going to say let's just do the flanges only because I don't want to cut too many holes in this cross section. Okay, and then that would mean I would have 3 lengths here, and then if we assume that this is 3 inches typical, then my length of connection would be 2 times 3 or 6 inches. Okay, and so that would allow us then to basically do a check. All right, so once we do that, now we can go in and we can look at our shear lag coefficient. Okay, so if we go back to table D3.1, okay, it's a lot of back and forth. You'll see why this page is actually a pretty good one if you're working in a cubicle or at a desk to have handy. This was, you know, for years I had this table on my wall next to me because I was constantly coming back and having to pull these values out. But we're going to look at, so we're down in case 7, okay, because we're a W shape. I'm looking at a flange connected with 3 or more fasteners per line in the direction of loading. Well, we meet that criteria by going with 3 flange bolts. So when we were saying we were thinking about doing 2 lines with 6 bolts in each one with the bolted web, I would violate both of these. Okay, and either one I would have to go up and do case 2. 7 wouldn't work. But because I've got 3 in a line, I can jump over to here and I know my U is going to be either 0.9 or 0.85. Okay, and so if I look at that for those particular values, all I have to do is take BF and compare that to 2/3 of D, and that will give us an answer on U. Now, if I don't want to do this check, I could just pull 0.85 and go and keep on going, but we'll go ahead and do the check. Okay, so if we look at it on here, so I'm checking, is BF greater than or equal to 2/3 of D? That's what this question mark is telling me. So my BF we know is 4.02 inches, and my D was 8.11, 2/3 of that value. So is 4.02 greater than 5.43? The answer is no. Therefore, my U is 0.85. Okay, now, just for fun with our arrangement, let's go check case 2. If we assume a bolt spacing of 3 inches, then my L we said was 6. And then we can do our X bar calculation per the commentary that this is D over 2 minus ZX over A. Gives me X bar for a wide flange beam. This is now 8.11 over 2 minus 13.6 over 4.44. This number is basically 0.99, about 1.0. Okay, and so that's my X bar value. So then I'm doing 1 minus 0.99 over 6. This is the case 2 equation. Gets me a value of 0.83. And you can see they're pretty close. There's a lot more calculation here than there was here, but you know, I'm allowed to use 0.85 anyway. If this had been something like 0.96, well, then maybe I use that value. But at the very least, this guy, I can always use the K7 numerical value. Okay, so that's how we know that K7 controls, all because of that note. All right, so now we've got a value of U. So let's go in and let's calculate our area effective. So for us, we're going to do 0.85. That's my U value. And then I do A gross minus, I have 4 flange holes. So it's 4.44 inches squared minus 4 times, here's the diameter of the hole, 3/4 plus 1/8. Okay, multiplied by then TF for this beam, 0.315. And I know that my effective area is 2.83 inches squared. Okay, so now I can do that check of 2.83 over 4.44. Is that greater than 1.2? Okay, so again, that's our check. If it's greater, gross yielding controls. If it's less, net fracture controls. 1.2 of 50 divided by 65. I have 0.637. Is that greater than 0.923? And the answer is false. So net fracture controls. So what we have to do is we have to recompute using a new AG min for our net fracture value. Okay, so let's figure out, well, what is AG minimum coming off of net fracture? Okay, I know it's a long process, but design is always a little bit involved. So let's go calculate AG min for net fracture. This is PU over shear lag, phi, FU, plus the area of the holes. Okay, and then plugging in all the values that we've talked about before. Okay, and you'll see one of the problems that we're going to have now is that we have 200 kips, 0.85, 0.75, and 65 for the first term. And then here's my area of hole. The problem is now I don't know TF because I have to have a size to know TF. It's an unknown value. Okay, now what I typically do in that case is I go back to my table, and I apologize, I closed the book accidentally. All right, and we look at kind of how these things are grouped. Okay, our original guess had us down in this grouping here. Okay, whenever I get into a net fracture case, often what I'll do is I'll move 2 sizes up, kind of as a guess to get me into will that work or will it not, especially for these smaller sizes. Okay, if I'm up in one of these bigger ones, maybe I only have to move up 1, but basically kind of take a guess that I'm going to go two groupings up or somewhere around double this load. Okay, just to kind of help me out. Okay, and so what will happen is we're going to go look for, kind of get a sense of, well, what are the TF values in that upper size that we're looking at? And if I slide over, that's this column here. And you can see I have TFs that are in a range of 0.4 to 0.46. So if I took just a guess at TF and said that, it's a 0.4 value, okay, that would be kind of a again, it's a guess. We haven't chosen a size yet. Okay, but if I took a guess of that as a 0.4, then that would correspond to a W8 by 24. We meet the minimum, and I plug that in up here, so that's what I'm doing is I'm plugging that guy in right there. Then I can calculate what is the gross minimum effective area for net fracture. Well, it's 4.82 plus 1.4 is 6.22 inches squared, and now I can come back in and find out, did my guess of 0.4, which was here, did the AG minimum meet it? And it did. It's 7.08 inches squared. So that's how I can kind of take a guess on what I would need. So then we know that we'll be okay for our net fracture calculation. Okay, and so that's kind of the process that we're looking at. Now we can also look in the same table that RY for this particular beam is 1.61 inches, and so RY is greater than R min of 0.8. So we're okay for the slenderness still on this particular problem, and we're okay for the AG minimum. So I'm going to use, this is where I would make a note that I need a W8 by 24, and that I would need 12 3/4 inch diameter bolts as a minimum in the flanges only. Okay, now, again, this is not a final design, but this at least gets me a size that now I can go run my structural model to be able to kind of work on. Okay, now, again, we have to check other things. This does not include other checks for strength, block shear, bearing, slicer, several others that we'll talk about later in the series. So there are other checks that have to be done, but these guys are controlled. I can tweak these by changing the spacing of the bolts or the diameter of the bolts. I can change that very, very easily. A ½ inch change in spacing gives me huge increases in capacities when we start talking about these. So these are the two that I got to get this guy set before I can fix those. Okay, so that's kind of what we're doing. Now, I'm going to show you another method to get you kind of that will get you close. It may not be exactly right, okay, and it generally gives you kind of it may not be the most economic, but we can go in to, whoops, took that page off by accident, that we can look at kind of a faster alternative. In section 5 of the book, okay, they do have tables for basically available strength and axial tension, but you got to be kind of careful because they make some assumptions in here. The first thing that we notice is that, we have, tables for I-beams, we have tables for T-beams, angles, whatnot, all contained in here. And what these are is these are tensile capacity tables for specific shapes. Now, the one that's really nice is the yielding criteria that I could very quickly come up this table. And if I look at, let's go find the right page, make sure I'm on 5065. We know we were kind of down in the W8 family. So and if we look, we can see that for gross yielding, 200 kips, this would be my W8 by 15. That's exactly what we saw. Okay, now the problem that we have is that we know that over on the net fracture calculation, they're estimating net fracture capacity is 162. But what they've done and what they don't cheat and what makes this table a little bit less than as useful as it could be is that they're assuming the effective area is 0.75 times the gross area, that you're losing 25% of the gross area to the holes that are being popped in this thing. Okay, so this is kind of, you don't know this until you design the holes. And so if my effective area is greater than that number, then gross yielding will control, and if the gross yielding parameter will control, and if my area is less than that number, then it will be the net fracture that will control. But we can use that kind of as a sense of, well, where are we at? Okay, and so my net fracture, if I came up and I slid up to this, then this says that if I met that assumption, at the minimum, I would need a W8 by 21 to meet my capacity. And then more likely, we might end up having to slide up again when we do our final check. But this gets you close. And an 8 by 21 versus an 8 by 24, there's not a lot of difference in the tensile capacity. Well, I mean, it's 30 kips, but in terms of relative size as a first guess, we're close. We're within a size or two. Okay, we're a lot closer than we were when we were down here at W8 by 15. So the table can be used to work that out a little bit. So according to this table, if we meet that criteria, I would need a W8 by 21 minimum to make that work. Now, again, we did the more detailed method that told me W8 by 24, but this W8 by 21 is a big one to be looking at. So just for, for posterity, that's what I'm kind of looking at, but that assumed area effective was 0.75 times the gross. Now, for our case above, my area effective we said was 4.82, okay, and my area gross is 7.08. The area effective then is about 0.68. Okay, so we're a little bit lower than what that table is. So whenever this number is lower than what's in the table, it generally moves you up a size or two as well to meet that. I'm close to 0.75, but I'm not quite there, so we're a bit low. Okay, so we can use that kind of, again, we're just looking for ways to get first guesses in design on this, okay? Okay, but basically this means that because I didn't meet that criteria, this gets us close, but you still need to thoroughly check net fracture once you've laid out the connection and looked at the holes and those kind of things. So you've got to be very, very careful, and that's kind of the moral of the story in all of these procedures. It's kind of there's a lot of moving parts in this, and it all kind of boils down to aiming for a gross yielding capacity, but then laying out the bolts, in such a way that allows me to get kind of a guess on the shear lag coefficient. And that's kind of the process that we're looking for. So like I say, it's a long problem, and this video is a little bit longer than the normal, but I hope it's made sense to you. It's a very important concept. We get into a point now where we can start kind of setting up spreadsheets to kind of automate this procedure, because you are in a mode of guessing and checking. Okay, but you can generate spreadsheets that will tally up these values for you, input, and then you can quickly verify what works, what doesn't. Okay, but those are a couple of methods that we can use for design to get first guesses on members that now let us to refine our model and thus refine our loads. And we're now, into that iterative process, but at least we have a size to kind of play with. Okay, all right, so anyway, that's what we have for today. I hope that's made sense. If you've got any questions, as always, leave us some comments down below, and we'll be happy to get back with you. And if you found this useful or learned something from it, toss us a like on the video, and then As always, be sure to subscribe to the channel if you haven't already, and we will see you all in the next one. So happy engineering.